Here we discuss partial primary balancing in locomotives. So see, this is a single cylinder engine with a piston within a cylinder, and this is the connecting rod, this is the crank. So as we have already discussed that actually we have to balance the inertia force due to the acceleration of the piston, and also you have to remember that we have broken up this connecting rod into two concentrated masses, and we have placed one part, approximately one third of the mass of the connecting rod at the piston end and two third at the crank tip. So the mass of the piston plus one third, approximately one third mass of the connecting rod is actually executing a reciprocating motion, and there is an inertia force generated Fi, which is m omega square r cos theta. Here m is actually the total reciprocating mass. In our previous lecture, maybe we have written it as m with a suffix r, but here we have dropped it for the sake of convenience. So it is m omega square r cos theta, and this is primary balancing because you remember that this is actually the expression of piston acceleration with the first term, and there is a second term omega square r cos uh, 2 theta by n. So we have not considered the second term, so it is partial primary balancing because we are only interested in balancing the primary part of the inertia force. Now if this is mi omega square r cos theta, so and if we add at the opposite side of the crank a mass b, so, and this crank is rotating at a speed of omega, angular speed of omega, then due to this b there is some omega square and mass of b, if we consider it as mass, and into omega square ob into mass of b. And if this is b, then this is, I write it again, if the mass is b, then omega square b is this length into b is the mass omega square r. So this is the centrifugal force, and if you take two components, this is b omega square b cos theta and this is b omega square b sin theta. Now if this b omega square b is equal to m omega square r, then along the center line this inertia force is balanced by this inertia force. So BB equal to MR, where B is the balancing mass and B is the arm at where this balancing mass is placed, and if this BB is equal to M multiplied by R, then there is a complete balancing in the along the center line. But perpendicular to the center line, this b omega square b sin theta is coming, and there is no one to balance it. So though you have balanced it along the center line, you have brought in a new component perpendicular to the center line. So what is done is along the center line complete balancing is not done. So this B is so selected that this is not equal to M into R, but it is CMR, where C is less than 1. So in this way what happens? The force along the center line is not completely balanced, it is partially balanced, but at the same time the unwanted component perpendicular to the center line is also less. So that is the objective of partial primary balancing. So in this case, now the net unbalanced force along the line of stroke or the center line is m omega square r cos theta minus b omega square b cos theta, and bb is equal to cmr. So 1 by, now the net unbalanced force is 1 minus c omega square r cos theta. If c equal to 1, then there is a complete balancing, but c is less than 1, so there is only a partial balancing, and the unbalanced force along perpendicular to the line of stroke is b omega square b sine theta, so c omega square r sine theta, and the resultant unbalanced force is this. The resultant unbalanced force is this. Yeah. Now, so if now this force which is perpendicular to the line of stroke, the perpendicular to the line of stroke is actually in locomotives. Due to this, the pressure between the wheel and the rail that changes with time, because this force acts in the vertical direction, this force acts in the vertical direction, so this force acts like this with a frequency of omega. So this force actually changes the normal reaction between the wheel and the rail. So this is also known as a hammer blow, and this limits the speed of locomotives, because if this reaction force is 0, then the wheel loses contact with the rail. See, this force is coming and on the bearings, and from the bearings it is transported to the structure which houses those bearings, and that is actually the body of the locomotive, and this force acts on the body of the locomotive, and this is actually b omega square b sine theta. So as theta changes, this force is like this, and when it is in the upward direction, the it decreases the reaction between the wheel and the rail, and when it is in the downward direction, the reaction between the wheel and rail is increased. So while selecting a speed of the of a locomotive, then we have to consider this hammer blow, because we don't want the reaction between the wheel and the rail to be 0, because then actually it jumps off the wheel, which is undesirable. So now here actually we discuss multi-cylinder inline engines. So multi-cylinder inline engines, in inline engines, all the engine center lines or lines of stroke, they are parallel to each other, and they all are in a single plane. So all this is one center line, or this is one center line or line of stroke, this is another line of stroke, this is another line of stroke, this is another line of stroke. They are all parallel to each other, and they are in a single plane. So, and here we are considering the primary and secondary part of the acceleration. So this is the primary part, and this is the secondary part. So for each of these cylinders, this is the force. So this unbalanced force are all along this lines. The unbalanced forces are all along these lines, but at one instant their magnitudes are not constant because theta is different for each of them. So we denote, if this angle we denote by theta, then this angle we denote by theta plus phi to 1. That is the angle of the second crank is theta, this theta, and the difference between these 2 and 1 is phi to 1. Difference between this third crank and the first one is phi 3 1. So this angle is theta plus phi 3 1, and this is how we name it. So, and this angle actually depends on the phi I1, that is phi 2 1, phi 3 1. This actually depends on the firing order. So now the unbalanced forces here, suppose, sorry, so unbalanced forces here in this direction, in this direction, in this direction. So this we call F1, F2 like this. So this is, suppose we call it F1, we call it F2, we call it F3 like this. Then F1 is m omega square r cos theta plus cos 2 theta by n. And for F2, this theta has to be replaced by theta plus phi 2 1. Cos 2 theta by n, cos 2 theta plus phi 2 1 by n. So for the ith cylinder, so it is theta plus phi I1, theta plus phi I1 twice. And for the nth cylinder, theta plus phi n1. Phi n1 means the angle between the nth crank and the first crank. So this is this. Now, and the resultant forces if you add these forces. So if you add these forces for the first term, then it is the primary unbalanced force, and if you add these forces for the second term, then that is the secondary unbalanced force. So the primary unbalanced force is this. Now this we can, for the ith cylinder, it is this. So this we can write like this. So for identical cylinder, since we have assumed that all cylinders are identical, so this Ri is R for all the cylinders, and Mi is M for all the engines. So Mi m omega square r is common for all of them. So we can take this out of the summation sign. So this is cos theta summation cos phi I minus m omega square r sin theta sin into summation sin phi by I. Okay, so for each cylinder it is like this for the ith cylinder, but all cylinders are having same mass. So ith cylinder mass and the I plus 1th cylinder mass and the nth cylinder mass, they are all same. So this is common for all of them. So this cos theta is common for all of them. So m omega square r cos theta comes out, and this is this. Similarly, m omega square r sin theta is common for all of them, and then sum of this. So for this Fp, that is the resultant primary forces or the sum of all primary forces, has to be 0, and the condition for that is summation cos phi I1 equal to 0 and summation sin phi I1 equal to 0. Similarly, for the secondary unbalanced force, the second part of the acceleration cos 2 theta by n, so mi omega square Ri by cos 2 theta divided by n. Now here m omega square r is common for all cylinders, cos 2 theta is common for all cylinders, n for all cylinders. So this is what you get, and the condition for secondary force balance, or here also it is primary force balance, is for that Fp equal to 0. So these are the conditions, and for secondary force balance cos twice phi I equal to 0 and sin twice phi I equal to 0. And for the kth harmonic, if you take this m omega square r cos k theta a k cos k phi 1 minus sin k theta a k sin k phi I by 1 k phi I1, then the condition for balance is this and this, that is for the kth harmonic. Because for the kth harmonic, if you take the acceleration as m I omega square r I, then a coefficient a k, and for the kth component say cos so this is actually for the kth harmonic k theta plus phi I1. So this ak is a coefficient, like for the secondary we are getting 1 by n, for the secondary we are getting 1 by n. So for other these things, other harmonics, there will be a coefficient, then cos k theta plus cos k theta plus I phi 1. Now you break it up and you get this. So k, for this k, actually for k equal to, so 4, 6 like this, or even. So we have only considered k equal to 1 and k equal to 2, but you can also consider k 4 and 6, and for that these are the conditions. And here now we come to shaking couple. So see here, these are the forces. All the forces are along the line of strokes or the center lines, but they are of unequal magnitude. And if you take this as your reference, since these forces create a moment, and that we know as the shaking couple. And if the resultant force is in this plane, in this direction, and the moment is perpendicular to this plane, because if you take moment of this force about this point, the moment is perpendicular to the plane. So CR vector is perpendicular to the plane of the FIs. So now if you take this distance as I, for the ith cylinder, the distance is xi1. That means this is actually x21, and this is actually from here to here it is x31. So from here to here is xi1. So now the moment is xi1 xi1 f1. I1 means distance between the ith center line and the first center line, that ith line of stroke to the first line of stroke. So Now xi fi. Now here fi is for the primary unbalance, you know, it is m omega square r cos theta. So m omega square r cos theta and sorry, m omega square r cos theta plus phi I1. So now if you break it up, then this is what you get. Here this xi1 is getting multiplied with the cos theta and sin theta values. So like this. So xi1 fi is m omega square r, then cos theta plus phi I1. So this turns out to be xi1 m omega square r, then cos theta cos phi I1 minus xi1 m omega square r cos theta this is sin theta sin phi I1. So from here m omega square r is same for all the cylinders because they are identical. Cos theta is taken out because it is also same. So xi1 cos phi I1 summation is there, xi1 cos phi I1 minus, and here this summation is there. So and the condition is this has to be 0 for Cp to be 0. Similarly for secondary unbalance, the condition is xi cos twice phi I equal to 0 and xi1 cos twice phi I1 equal to 0, summation of that, and xi1 sin 2 phi I1 summation of that is 0. So here actually what we are doing, so you remember actually we are calculating moment about this point. That means actually we are bringing all the forces here, we're bringing all the forces here and considering it as a concentrated force system, adding the forces vectorially or adding the forces to get the unbalanced force, and we are adding the moments to get the moment. So here you see actually we have brought the forces to the reference plane. So if this is the reference plane, then we are getting this as your Fr, the resultant force, whether there is Fr is, therefore Fr there is a primary resultant force and the secondary resultant force, and Cr also for primary and secondary. Now what you can do is, since there is one Fr and one Cr, so you can shift this force parallelly to some other point Fr into, so that the Fr into Xr is Cr. So you, if you shift it here, then you need not show this moment. So now it depends. Xr is in general a function of theta. In general, that's function of theta, but there are some interesting special cases. So, and in some cases if you get Fr equal to 0 but there is some Cr, then it is a case of pure couple unbalance, pure shaking couple unbalance. So we'll look into the special cases little later. So now for the time being we stop here.